Our mission is to be the technology which closes the gap of that missing piece in the puzzle of energy transition. We are trying to be the fastest in the market.
This is EnergyCast, and I'm Jay Dowenhauer. Today we're talking about using CO2 for energy storage. I've covered a lot of energy storage technologies on this show, and I'm a sucker for solutions like this. CO2 checks a lot of boxes for storage, and my guest believes their technology is key for a low-carbon energy future, though maybe not in the way you'd initially expect. You see, carbon dioxide, the molecule, has some unique physical properties. Unlike air or water, it is particularly squishy. It can be compressed easier than ambient air, and my guest says that's why they are using it as their choice of medium for storage. He says compressing CO2 and storing the heat you generate when a gas is compressed can result in a remarkably efficient battery. The compressed liquid CO2 can be stored in medium pressure tanks. The question then becomes, what do you do about the uncompressed CO2? That gas is contained in a large inflatable dome, which gives the company their name. My guest says the system is designed to be closed loop, meaning you'd fill up the dome with CO2 and it would cycle back and forth endlessly. That may be a little disappointing for listeners who were hoping for a long-duration battery that would reduce CO2 emissions at the same time. We discussed the potential for this battery to pass through CO2 on its way to long-term carbon sequestration. It seems like a good fit. These guys have compressors sitting on their premises, and compression is one of the most energy-intensive parts of disposing of CO2. He says that's certainly part of their future plans, but for now, their mission is to show how carbon can be a perfect complement to sustainable energy. My guest today is Claudio Spadaccini, founder and CEO of Energy Dome, an energy storage company based in Milan, Italy. Energy Dome was founded in 2020. They commissioned their first facility this past June. Claudio and I spoke at length about the need to use simple, off-the-shelf technology to ramp up quickly, which appears that they did. I hope you enjoy my conversation with Claudio Spadaccini. We're here with Claudio Spadaccini, founder and CEO of Energy Dome. And Claudio, this is a very interesting technology. Tell us, what makes CO2 a natural solution for energy storage?
Hi, very nice to talk to you today, and thanks for inviting me. The need of long-duration energy storage is the missing piece in the puzzle of energy transition. So in order to get to, let's say, a full decarbonization of the planet and to reduce the CO2 emission, there are just two ways, which are, let's say, nuclear fusion or long-duration energy storage plus renewable. And the missing piece in the puzzle is a technology which can allow arbitrage and which can allow energy shifting to be competitive enough in the market to supply baseload power, baseload renewable power to the grid. So what I feel is that the CO2 battery is a solution which can be a product which can be deployed in the market at scale with the same size of a solar plant or wind turbines, and can be deployed fast and can unlock the possibility to deliver baseload green power at a very low cost into the grid.
Claudio, I've spent a little bit of time with CO2, especially carbon capture and storage. Back in Texas, I was executive director of a carbon capture and storage association. One of the things we talked about when we were talking about carbon capture and storage is CO2's ability to be supercritical, right? Its ability to be kind of a gas and a liquid. And I think that's what you're emphasizing, not only the climate aspects and the energy storage potential, but CO2 itself as the medium for storage. It has some unique unique properties I don't think many people are familiar with, but you're taking advantage of in this technology.
Yeah, sure. The idea I got to use CO2 to store energy is exactly in that regard. One of the well-known used technology in the energy storage space is compressed air energy storage, which uses just ambient air, which is compressed at a relatively high pressure between 70 and 150 bar, and then stored underground in stored cavern because of a big issue, that is that air, if compressed at high pressure, is still quite low density, and you need quite a large volume to store high pressure air. One of the solutions to that, a technology which tried to improve this technology, has been liquid air energy storage, which has identified solution going very low temperature. By going down to minus 180 degrees C, you can liquefy the air and store in relatively small and cheap vessels. The cons are very low temperature, lead to cryogenic material for all the equipment that you need, and this increases the cost and to reduce the efficiency of the site. The idea I got is to use liquid CO2 because liquid CO2 can liquefy at ambient temperature. CO2 can be liquefied supercritical around 20 degrees C. You can liquefy CO2 at 60, 65 bar, and that is super convenient to store energy in a carbon steel, very common material, medium pressure vessel, which are cheap and real, make this CO2 storage technology very competitive in price and also very efficient.
Right. So you're literally compressing the CO2. And this is different from things we've talked on this podcast before about liquefied natural gas. And that's compressed. It becomes liquid essentially by freezing it. In this case with CO2, though, as opposed to natural gas, you're physically compressing it as opposed to cryogenically making it switch phase to liquid.
Right. And you are exactly right. And the difference is that, we can make CO2 liquid at ambient temperature. And as a consequence, the components are really cheap. We use carbon steel, we don't use stainless steel or cryogenic material. In order to liquefy the CO2, we also have to extract some heat, but we can do it at ambient temperature and store in a water basin and then release back that heat when we have to vaporize back the CO2 in the discharging process before to heat up into the thermal energy storage and discharge into the expand, which produce back power to the grid. It is a very efficient process which works with existing component which can be supplied from existing supply chain of the shelf component, and that's also make the technology one of the few, or maybe I would say also the only one technology which is available aside the lithium-ion batteries to go in the market right now, because also time to market is very important, and the energy transition is not only about decarbonizing the planet, but it's very urgent. We need to do it now. That's the point.
Right. That's a point I've always said is like, what can you do to reduce CO2 now? So let's talk a little bit about round trip efficiency, right? It takes energy to compress, and then you're getting the energy back by running the expanding CO2 through a turbine.
Yeah, the principle is that we compress the CO2, and by compressing the CO2, we store the energy in two ways. One is pressure, and the second one is heat. We compress the CO2 from atmospheric pressure to about 60 bar and a bit less than 400 degrees C, 350 degrees C. After that, we cool down the CO2, which is under pressure, in a thermal energy storage system, which store the thermal energy. After that, the CO2 is liquefied and stored into high pressure liquid CO2 vessels. So the energy is stored, a portion, let's say, in pressure and a portion in thermal heat, which is available for the discharge. When we go back, we just go symmetrically on the same process, but in the different way, and we just evaporate back the CO2 by taking back the heat, which we store in the water basin. And after that, the pressurized CO2, which is vaporized, flow through the thermal energy storage and take back the heat, which has been stored there, and then enter at high temperature and high pressure into the expander and supply back as much as 75% of the electricity which has been used from the compressor to the grid. So The process is very high efficiency. 75% is almost the same efficiency as lithium-ion batteries. Yes, at the beginning, lithium-ion batteries are maybe better because they can start at 85, but the entire life, till the end of life, after let's say 4,000 cycles, the average efficiency of a lithium-ion battery system is in that range.
Yeah, 4,000. I know a lot of modules that can't get to 4,000 cycles. So you're saying about 75% round trip efficiency. That's really important because a lot of PPAs, the power purchase agreements, especially when it comes to energy storage, have a floor for round trip efficiency. If the round trip efficiency, no matter how much you can store, how much capacity you've got, if it's too low, you can't get a PPA for that. I guess the idea is you've wasted too much energy or something. And then there's also a thermal component, which I was just expecting compression, decompression, right? So what happens with the thermal energy again?
At the discharge of the compressor, the CO2 exit, which is pressurized at about 60 bar and 350 degrees C, that high pressure flow of CO2 flow through thermal energy storage, which is a device. The thermal energy which is inside that flow and cool down the CO2 close to ambient temperature, about 30 degrees C. That heat is stored inside that system, which can work with different medium inside, like thermic oil. And then at the exit of the thermal energy storage, this CO2 is condensed into a condenser, and the heat of condensation is accumulated in a water basin and then is liquefied.
How much capacity are we talking about? Hundreds of megawatt hours? When the CO2 is expanded, the dome that we're talking about is almost like an inflatable building, right? It's kind of this inflatable structure that's very large, right?
Absolutely, but the size of the dome is not a big issue in our view. And the size of our product, the CO2 battery, which we are putting in the market, is 200 megawatt hour as a first product, which we are proposing to the market, is 25 megawatt, 10-hour duration module, which can be also deployed in multiple modules. So we can easily install up to 5 or even 10 CO2 batteries, one beside the other, like a wind turbine. So the business model we have in mind is the wind turbine business model. So we wanted to supply to the market a standard module out from a catalog, which are very standardized, repeatable, no technical risk, so that our customer quite soon after we will deploy several dozens of units in the market will also get access to very low cost of capital. In our opinion, this is the way to go. So standardization and getting multiple modules which are identical implemented in the market is key. Like when you have to build, for example, a wind farm, maybe you can have a wind farm with 20 wind turbines, which are identical. It doesn't make sense to make a custom design, much bigger wind turbine, because that would not be competitive. Regarding the land use, the CO2 battery is the only one parameter where we are not best in class, is the land occupation. But if you look at that parameter from the energy transition perspective, we just occupy something like 7 to 8% of the solar PV field, which we need to charge our CO2 battery. So if you take this, since energy transition is about to use a lot of land and a lot of space to generate a lot of renewable power to decarbonize the planet, let's consider that the CO2 battery to store that energy and to transform that energy from peaking to baseload green energy is about 7 to 8% of the space you need to produce that. So this is something that is not a bottleneck in the process of decarbonization through baseload renewable energy.
That's a good point, because I think solar is 5 acres per megawatt and wind needs to be spread out,
And we can accumulate as much as 5 kilowatt hour per square meters. If you make the comparison, this is something that is not the bottleneck.
Claudio, I know you have a presence here in the United States. You're in Milan. Let's talk a little bit about the business of this. And I know the business of energy storage, and especially since there's a price on carbon in the EU, these things work a little bit differently. But what is the best business case for this type of energy storage? I always go to energy arbitrage. There's a lower price of energy per day. You'd store during that. The higher price you would discharge. What do you think works best for Energy Dome?
Thank you very much for that question, because this is my opinion at the point. Arbitrage arbitrage seems to be obvious business case in energy storage. In reality, it doesn't exist right now. All the energy storage projects which have been deployed in the market till now have been projects which get revenues out from capacity, out from grid regulation. With that technology, we can allow arbitrage projects to be competitive almost all around the world. We can supply also the other services.
Yes. One of the things I've been talking about with a lot of my guests is this idea that renewables have gotten to the point where you are starting to have negative energy prices. You're having to start to have curtailments of renewable energy because too much renewable energy is on the grid at a single time in the United States. A figure I was told was up to 30% of renewable energy can be curtailed. And so you need something that can absorb that excess energy. Otherwise, you're going to lose it, not to mention all of the renewable energy credits that you would be losing by having that energy dumped. So I would have to imagine is one of the big solutions that a lot of developers are hoping for, right? Something that can absorb when we need to absorb excess renewable energy.
Yes, we have a really, let's say, specific discussion with potential customer, with specific project where they really have the asset working with a lot of curtailment, and that is not good. But in order to have a solution, the solution has to be cheap enough and efficient enough and long lifetime enough to be competitive. So up until now, lithium-ion batteries have been a great technology up to 2 hours, maybe 4 hours. And solar PV is naturally something which is 8 to 12 hours. Having the right technology, we can unlock the market. It's like Tesla has unlocked the market for electrical vehicles, which was not believed to be possible before. So what we aim to do with our technology, which is very competitive and high efficiency, is to unlock this energy shifting market that can really be a huge $1 trillion opportunity, but need the right breakthrough technology to be available. And I'd like to add, it is possible to manufacture, our CO2 battery in every country, in the US. And that is very important because we don't depend on any kind of rare earth material or rare metal. We just use steel and some water and some CO2 and nothing more. Every country right now, nowadays, is very much looking not to be geopolitically dependent on material which cannot be find inside the country. And the US is very sensible to that. And also the new regulation which has been issued with the tax credit to the technology which can be produced in North America. Our technology can definitely be fully produced in North America or in Europe or in Australia.
Yeah, it seemed to be like it was a lot of, I guess, what we would call off-the-shelf components, right? Let's talk a little bit about the CO2 usage. And I think that a lot of people's ears probably perk up when they hear the idea of a CO2 battery. Oh, we're doing something about CO2. We're possibly going to sequester it. It sounds to me like the design as you have it has the CO2 in more or less a closed loop system. The same CO2 is being deflated and inflated, but there could be an opportunity, right, for passing through CO2 maybe on its way to long-term sequestration. You're compressing the CO2, and that's always been the most energy intensive, it seems, part of the process aside from capture. If you've compressed CO2, then you could essentially send it down a pipeline to be injected. Of course, you lose that CO2. But if you were in a system where we're hearing a lot about direct air capture, and I think even carbon capture from fossil plants is starting to get a little bit more notice these days, is there a situation or a scenario where you would be taking new CO2, running it through your system a little bit, maybe compressing it on and sequestering it so that you are net reducing CO2 as you're operating? Does that make sense?
Yeah, that's a very good point, because if we look at our embedded emission in our system, those are already by far lower than lithium-ion batteries in terms of embedded emission. But we are also in discussion with potential supplier through direct air capture, or maybe even a sequestration of the CO2 coming from other renewable energy plants like geothermal. Some geothermal plant has some CO2 emission. So we would like to improve our embedded emission by charging our system, which you already said is a totally closed system. And so we have to fill up the system only once at the beginning of the life. But we are considering to try to do it with with direct air capture or with, let's say, sequestration from geothermal plant, which could lead to a net negative emission of the plant from the very beginning. And this is really one of the things that we are looking at.
Right, because I'm thinking about this. I'm guessing it doesn't take as much time to charge as it would to discharge, right? The idea is you want to charge quickly and discharge slower, right? So you're not overrunning. There could be a lot of downtime when everything's just kind of sitting still. You could be using those compressors to compress more CO2, and you are getting a price for sequestration as well, right?
Yeah, that could be technically possible. We are really looking to work in the green space. Our mission is to be the technology which close the gap of that missing piece in the puzzle of energy transition. Carbon capture and sequestration is something that it's very worthwhile in this transition. But yes, it is a transition. It's not the final solution, at least according to my view. So in my view, the final solution is the green production. So we are targeting to solve that big challenge, but at the same time, we are trying to challenge, that issue today and to be the fastest in the market. The other point that I see is that working on carbon capture and sequestration, normally you work more about projects which are different one from the other. So our CO2 battery is intended to be a product, 25 megawatt to 200 megawatt hour product, which can be purchased from a catalog like you buy a wind turbine. And that is very important because these unlock the possibility for customer to access, not today, but as far as we will be able to deploy several dozens of our plant in the market, we will get access to very low cost of capital. And this is key. If you look to solar and wind, one of the key of success of those technology has been to be very standardized technology. And those technology have got access to a very low cost of capital. We want to go that direction. We want to offer to our potential customer, utilities and IPP, a solution that will unlock them the possibility to have a very high return due to low capex, high efficiency, long lifetime, but also very low cost of capital. That is a key of success from our perspective.
And so in your business model, you don't expect to own and operate. You're a vendor, at least at this point, just so you can move faster. I assume.
Yeah, absolutely. This is our business model. Obviously, if hopefully we will succeed, since this market, which we could potentially unlock, is a potential $1 billion market, the growth could be unsustainable for a company which goes along. So in our business model, to grow as an OEM at the beginning, but we are also looking to potential JV or to potential agreement with large player in some geography to facilitate and accelerate the growth of the company, because the technology is ready. It's just to be deployed in the market. The market is huge and we cannot grow organically as fast as the market needs.
Understood. And so how close are we to commercialization? I mean, the CO2 is available, the equipment's available, the need is there. So how close are we to starting to see these energy domes around the world?
We started operation of the company in February 2020. Less than 2 years and a half, we've been able to put in operation our first commercial plant, which is not a full-size commercial plant, but is a commercial plant. It's not a small demo. This is a 2.5 megawatt, 4 megawatt hour plant, which is working almost every day. We communicate to the grid operator in Italy, which is our program for next day. And we say when we charge, how much do we charge, how much do we discharge. And this is a plant which is operational. We did it in less than 2 years. And this is due to two main things. The first, technology is pretty simple. The process is pretty simple and is fully based on off-the-shelf component and existing supply chain. And the second is that the founding team of the company has a long experience and very deep experience in turbomachinery and process engineering. So starting from that, now we consider that the technology has been fully de-risked. We expect that we will be able to sell the 25 megawatt full-scale 200 megawatt hour plant at 75+% around trip efficiency. We are just beating. We have already purchased the 25 megawatt turbo machinery for the execution of the first full-scale project, and we are raising capital, and we are trying to answer the many requests we are getting from all around the planet with a focus both in North America and Europe to try to be in the market with that product as soon as possible.
Well, I'm always a sucker for storage technologies that aren't always chemical batteries. So this is a really novel approach. I'm really excited for you guys. All right, Claudio Spadaccini, Energy Dome, thank you so much for your time.
Thank you very much, Jay, and thank you very much for inviting me. It was a pleasure to talk to you about our technology, and thank you very much.
That was Claudio Spadaccini, founder and CEO of Energy Dome, an energy storage company based in Milan. Claudio says their technology was recently verified by a third party, making commercial operations easier as they engage clients around the world. I want to thank Claudio for his time, as well as Henry Braffman at Antenna Group for setting this up. I've worked with them more than any other shop. You can find plenty of pictures for this episode on Energy-Cast, as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 151. Be sure to join us next week when we take a new look at the potential of wave energy. Until then, I'm Jay Downhauer. We'll see you next time.